So today we'll be starting off talking a little bit about vector fields. Remember yesterday we dropped off with this equation which basically says that if given a curve, first of all, like there are a lot of things undefined in this equation for like that we need to like take note of. One is this whole issue of like what gamma is. So what exactly is the curve and how are you going to put it across in that sense, like what are you exactly talking about? We just did discuss some things yesterday as to like how gamma is like a kind of a dummy of function kind of thing, just to keep a track of like what your curve could represent. So it's but if you look at it more specifically, okay, your gamma or the curve. So this is like again, it's like because of the nature of this subject itself, it is kind of like hard to define any object from just one way and get a like a complete understanding of the object. Sometimes we need to understand it from one way and it's not clear, so we need to come back and then we need to go front again. So it's like a multiple way journey. So it's like so similarly, so for example in this case, you have your gamma uh, which can be defined in the context of a vector field as this. Okay, so the curve is basically something like so what this idea represents is something that is very hard to capture using words, because it is okay. So I'll just uh, put this across. So suppose you have a given curve, right? And apart from like just the geometric picture of the curve itself, you can also talk about some sort of a flow of like a point from one point in the curve to another point. So you can say this is gamma of 0 and this is gamma of t, right? So what you can do now is uh, you can do this transformation of gamma gamma 0 to gamma t, and this function this transformation essentially is given by it's called as a flow. It's called as a vector. It's called as a flow, and it is given by a vector, like a vector field essentially. So what happens here is, remember we spoke about the basis existence of a basis at each point on the vector space. So we construct a basis in such a way that you get the tangent, I mean the directional derivative according to that basis at each point, right? From now, the idea is you're freely floating that basis along the curve, but in order to move the basis along the curve, we need to make sure that we are doing it like homogeneously, in the sense t becomes a homogeneous parameter. So now what does that mean? How does that come into the picture? Like what are we going with that? Where are we going with that? Is something that is pretty abstract. Okay, so the idea of having one dummy variable and taking the derivative of a curve with respect to that variable and calling it equal to the directional derivative. Okay, so what you can now do is to, okay, so if you just apply it to a physics problem, right? what you can do is you can just say that your curve is governed by your directional derivative. So that is this uh, becomes your curve, the definition of your curve. How, if you look at it, okay, first of all, your f is not a function of t. That is understood. F is completely independent, t is completely independent, right? So when you look at it, this is nothing but you have the directional derivative at a random point t. Yeah, at a point t naught, and then you're integrating it from, say, 0 to t, right? So it essentially defines your whole curve if you look at it. So you have the tangent at each point, and you're moving the tangent along each point of t, and then you're like defining the whole curve in this particular manner, right? Because the integration is nothing but like you're just joining together and linking together different points. So wait, uh, did am I audible now?
Hey, your video is getting stuck.
I know, I
And your
know.
voice is also breaking. I'm not sure if it's because of internet on my side or.
Okay, I
Yeah.
think it's mine. It's definitely mine because all of you are facing the problem. So just give me a second.